The Laplace transform is an incredibly useful tool when we're trying to solve differential equations. The equations that we see it applied to most often are those that show up in physics. So in order to use the Laplace transform, we first need to understand what it is. So today we're going to talk about the definition of the Laplace transform. In order to know what the Laplace transform is, we first need to know what is a transform. Well, a transform is an operation that transforms a function into another function. In your calculus classes, you've been exposed to two different transforms, namely the derivative and the integral. The derivative takes a function like x squared and transforms it into another function like 2x. Meanwhile, the integral takes a function like x squared and transforms it into another function like x cubed divided by 3 plus some constant. These two transforms that you've been exposed to before possess something called the linearity property. That means that the transform of a linear combination of functions is a linear combination of the transforms. So when you were learning about derivatives and integrals, you knew that if you had two things added together, you could take the derivative of each of them and then add together your two derivatives, and that would be the answer. And similarly, whenever you had a plus sign or a minus sign, you could break apart integrals as well to make your life easier along the way. That's due to the thing called the linearity property. We're going to look at a particular integral transform, namely the one where we take the integral from 0 to infinity of some function k of st times a function f of t dt. And you might remember from calculus that when we want to take the integral from 0 to infinity, we can take the limit as some value b approaches infinity of the integral from 0 to that value b. And then we leave our k of st and f of t dt all the same in our integral. Now you might be wondering about this function k of st that's thrown into the integral with f of t. That function is called the kernel of the transform. For our purposes, you won't need to worry about that kernel for a while. Just be able to identify that that is, in fact, the kernel of our transform. So now we can give the full definition of the Laplace transform. So we're going to let f be a function defined for t greater than or equal to 0. Then the integral from 0 to infinity of e to the negative st f of t dt is the Laplace transform of f of t. And that's provided that the integral converges. And what we mean by that is that we get some value for our integral. We don't get infinity, we don't get negative infinity, and we don't end up in a does not exist category. So the kernel of the Laplace transform is e to the negative st. Now, just a little bit of notation that we're going to use from here on out. When we talk about the Laplace transform of lowercase f of t, we're going to denote that with capital F of s. Since s is an independent variable in our kernel function, our Laplace transform is going to be dependent on that value s, since we're only integrating with respect to t. So that's why s is an independent variable with that capital F function that denotes the Laplace transform. Similarly, if we take the Laplace transform of g of t, lowercase g there, we're going to be writing that as the capital G of s. And not surprisingly, the Laplace transform of lowercase y of t is going to be capital Y of s. So let's look at what the Laplace transform of the function, simply t, would be. So what we're going to be doing is taking the integral from 0 to infinity of e to the negative st times t dt. In order to integrate this, we're going to need to use integration by parts. So we'll choose u equals t, since we can take the derivative of that incredibly easily, and it gets simpler when we do. And we'll choose dv equals e to the negative st dt, since we can integrate that. So taking the derivative of u, we get du equals dt. And taking the integral of dv, we find that v equals negative e to the negative st divided by s. So proceeding with integrating by parts and plugging these in with our u times v minus v du. So we'll have negative t times e to the negative st all divided by s, evaluated from t equals 0 to infinity, plus 1 over s times the integral from 0 to infinity of e to the negative st dt. Since e is raised to the negative st power, and s is a positive value, then we know that our e to the negative st is actually e to the st positive exponent in our denominator. And when we put larger and larger values in for t, the denominator is going to outpace the numerator. And eventually our denominator will be so large that it will make that fraction go to 0. So all we have to worry about is this second integral part, because the first part goes to 0. Now we can recognize this second integral as being the Laplace transform of 1. So what we really have is 1 over s times the Laplace transform of 1. Now the Laplace transform of 1, we could go through and work it out and see that it equals 1 over s. I'm going to save us that work for now, but feel free to go back and take a look at it and do that work yourself. So we find then that the Laplace transform of t is 1 over s squared. A couple of things to note. When we're taking a look at the limit as b approaches infinity, taking an integral from 0 to b, a lot of times we don't write that out, and instead we just write infinity as the upper bound on our definite integral situation. What we're really doing is taking that limit when we do that. So we're not actually plugging in infinity, we are in fact plugging in larger and larger values as they approach infinity and observing that end behavior. So another thing to note is that the Laplace transform is a linear transform. It's an integral, and so we can take integrals apart at sums. So the Laplace transform behaves in this linear form, and we have that linear property that you've grown so fond of with derivatives and integrals along the way. Also, so that we don't have to work out examples like this one that we just did, or the Laplace transform of 1, or the Laplace transform of any really common functions that we're going to run into along the way, or that you run into in physics situations. What we end up doing is saying, hey, here are the transforms of some basic functions, and you can always go back to these. Unless you're being asked to show that the Laplace transform is this for one of these things, you can get to a point where you can say, oh, I have 1 over s times the Laplace transform of 1, and I know the Laplace transform of 1. It's in this table of values that I have. So the ones that we know that we're going to be able to use as our transforms of some basic functions are the Laplace transform of 1, which is going to equal 1 over s, of t raised to any power n is going to actually end up being n factorial divided by s to the n plus 1. And that holds true for n equals 1, 2, 3, as high as you want to go with n. And actually you can note that that happened when we took the example of the Laplace transform of t to the first power. 1 factorial is 1 divided by s to the 1 plus 1, or s squared. would be our Laplace transform, and that's what we found in our example. If you're trying to take the Laplace transform of e to the at, well, that's going to equal 1 over s minus a. If you're trying to take the Laplace transform of sine of kt, that's going to equal k divided by the sum of s squared and k squared. If you're trying to take the Laplace transform of cosine of kt, that's going to equal s over that same sum of s squared and k squared. If you're trying to take the Laplace transform of the hyperbolic sine of kt, it's going to be k over the difference of s squared minus k squared. And if you're taking the Laplace transform of the hyperbolic cosine of kt, it's going to be s over that same difference of s squared minus k squared. So we're going to talk about when does this Laplace transform exist and not. In order to do that, we need to know about exponential order. So a function f is said to be of exponential order if there exist constants c and capital M greater than 0 and t greater than 0, such that if we take the absolute value of our function f of t, it's less than or equal to m times e to the ct for all t greater than our capital T. So basically, thinking about that graphically, we're looking at this and we're noticing that the function t here in my first graph is of exponential order because t is less than e to the t always. So we can say, you know what, c and m's 1, c's 1, and capital T, we'll just say it's anything greater than 0, and this is going to hold true. Taking a look at the function, say, e to the negative t instead, taking m as 1 and c as 1 again, our function does eventually fall below our 1 times e to the 1t. And so it is also of exponential order because that value where it falls below, begins falling below, that value we can choose as our capital T value, and then our statement is true. So my first two functions, the left and the center one, both of those are of exponential order. Now let's take a look at the one on the right, e to the t squared. So if I take 1 times e to the ct, any constant, I get my purple graph there. And if I graph e to the t squared, it becomes that pink graph. Now, it's important to note that no matter what I choose for m, no matter how large that value is, this is eventually going to happen. And it's going to happen for any value of c that we choose along the way. At some point, my function e to the t squared is going to be greater than my function e to the ct. Since that happens, I can't name a value, capital T, where when I look at all the values of t to the right of that, all the values of t greater than that this function falls below that exponential function of e to the ct. Since that's the case, this function is not of exponential order. So when you're trying to decide if something's of exponential order, a really great way to do it is honestly just to graph it. Just plug it into a graphing calculator, plug it into any of your favorite graphing utilities, and take a look and see what it looks like compared to some exponential function e to the ct. So now let's talk about the existence of the Laplace transform. So we have a theorem that tells us about sufficient conditions for existence. If f is piecewise continuous on the interval closed at 0, so 0 is included, up to infinity, and it's of exponential order, then the Laplace transform of that function f of t exists for s greater than c. And in this case, c is the c that it's exponential order for. All right, so we're working with that. And we also have a theorem about the behavior of the Laplace transform of f as s approaches infinity. If f is piecewise continuous on the interval from 0 to infinity, 0 included, and of exponential order, and it equals the Laplace transform of f of t, then the limit as s approaches infinity of capital F of s, so of that Laplace transform, is going to equal 0. So that's all we're going to talk about for now about the Laplace transform. We'll be talking more about ways to use it and things that it has as far as properties and everything in future videos.